Yeah, welcome back again. Last time we looked at the introduction to feature engineering, looking at the differences between feature selection and the feature extractions. All right, so we want to look at the feature selection methods, and one of them is called filter feature selection. So that is what we're going to look at today. And like I said before, for filter methods, it uses statistical measures such as correlation, ANOVA, F-value, which I mentioned then, and also mutual information to select features for machine learning processing. All right, so we're going to briefly go through the implementation. How do we select feature properly for machine learning? So this is a complete implementation of feature selection using filter methods on a SQLM low database data set. We're going to use low diabetes data set to perform this implementation. All right, so the first thing we're going to do is load our data set first. Run this. So when we run this, we have our database showing. So we're going to load database called load diabetes. This database. So we're going to load it from SQLM, and we're going to import select k-best to choose the best result. So we need a F regression and mutual information regression. So just bring in those functions from the library out. Then we call our database here. I mean the data set here. So assign x to x and y to y. So our feature name as shown here. So looking at the data set, we have age, we have sex, we have BMI, we have BP, we have S1, S2, S3, S4, S5 to S6. So these are the data set we have here. Okay, so this is our original shape 442 by rows and 10 columns. All right, I think 10 columns here. Okay, all right, so now this is our data set basically. I want to see how we can select feature from this data set now using the three methods aforementioned above. So the databases contain 442 patient records with 10 baseline variables, which are called features now. So age, sex, BMI, blood pressure, that's a BP, and 6 blood serum measurements. Okay, and our target variable is there, the quantitative measure of diseases progression after 1 year. So that is target. All right, so you can see our database of target here. All right, so we want to process this gradually. So using our univariate feature automation method now, which we mentioned. The first method I want us to look at is called correlation coefficient, which is a linear relationship. So we calculate using Pearson correlation method, technique between features and targets. So we call our correlation here. All right, so we print out the value and we see correlation between them. Then we plot our figure to see which one is the is best. So looking at it now, we can see that the BMI has highest correlation. I mean highest level. So we are followed by S5, followed by BP, followed by S4. Okay, so we can see those ones. So the other one down, they are very insignificant, right? They have very low value, so they are not really doing well. So you can see the table here. So you can see the table here. So BMI S5, PP S4, these are the one doing well. You can see this absolute correlation coefficient now we're having here. So this is the first method under this particular filtering method. Right. So the measure, this measure actually linear relationship between each feature and target, and the value ranges from -1 to 1, which is absolute value shows strength. When you have 1, we have very high strength, and towards the minus, we have a low strength. Okay, so this is simple, but misses non-linear relationships actually. Okay, so we can see here how we do. So when you move further quickly, you see that we have other method called ANOVA F-value linear dependence. Okay, so we use our select k-best here to find our k5, and we select our transform the very features here. We have f-score, p values. So we create data frame, and here we pass our value inside. So we sort it out and we print our result. Now from here you can see our features here, and we can see f-score here, p-value here. So based on this one, we can see that BMI, S5, BP, S4, they are very highly significant here. Can you see? At the same time, their F score is very high, right? While others are very low. So you can see that something seems to be very similar to what we had in the first method there, upper there. So which means that these particular 4 features, they are highly significant. I mean, very, very relevant to machine learning analysis. So we are going to see that as we journey gradually towards the end. So it shows that a certain linear dependency between features and targets, and a higher F-score indicates a stronger relationship, which is linear now, and the p-value shows statistical significance of those features one by one. All right. So if you move further a little bit, you see that we have mutual information for non-linear dependence. Okay. We select our top 5 mutual information here, okay, by using a case of 5, then we transformed it, and then we pass our score, get our score. So when you look at the feature we print out here, we have a mutual feature result here. Feature, you can see that here we have 0.170, 0.14, which is this highest one. BMI also show S5, S4, and S6 also included. So these are, the rest are very small values. So the higher the values, the better. So the detect here both linear and non-linear dependency here actually measures how much information about target is contained in each feature. This is more general than correlation, but computationally more expensive. All right. So let's compare the result now and see what we are talking about. So we can compare and visualize the result now by just creating a visualization for them, right? So we plot a comparison table. First, combine all the score together, feature for each of them, F1 score and mutual info. So we print out the result here. You can see this correlation, this F test, this mutual info, right? So now you can see that we don't just want a particular feature that is lopsided. We want the one that cross across all the method we are talking about now, all the 3 methods. So sometimes a feature can be very relevant in one particular method, but not relevant in the other method. That feature is not consistent, okay? Which means it will not be useful when it comes to machine learning. So, but if a feature is relevant throughout all the methods, then that is one of the best features we can use. So in this case now, we have our BMI, which is very high here for both F-test and mutual info. You can see that it's still high also for correlation. I also see our BP also is high also. You also see S5 is high for both, and also for correlation. You see S4 also similarly, and they also see S6 also not too bad, all right, while the rest are not doing well at all. So now normalizes score. This approach normalizes score from different methods to 0.1 range. Okay, it combines ranking to find features that performs well across all methods. That's what we're talking about, and reduces bias from any single selection method. So this method actually helps us to reduce bias from any single selection method, which means that we are able to know that a consistency feature which is consistent across all methods. So that we can select the best feature now, yes, using our k-best method, so that we can know that this feature is the best. So let's look at the best feature now by using this simple method. So here we can combine together. We see that our best feature here is called BMI, okay, followed by S5, followed by S4, followed by S6, and lastly BP. So these are the best features so far. So, and you can see here we have a BMI, S5, S4, S6, and BP. So these are the selected features that we have now. The analysis typically identify this as the most important features, all right? And the body mass index, body serum measurements, average blood pressure, that's the BP here. We have a blood serum measurement and blood serum measurement 6 also. So these are the features we have here now. Okay, so in summary, filter methods are fast and scalable. All right, different methods may select different features. Combining multiple methods gives more robust selection. Always validate selected features with downstream modeling. So using combine them together is give us a lot of give us broad understanding of each features and how they are consistent across many methods. So we don't just say okay, because it's good in a correlation, that means we can just choose it. No, we have to test it across multiple methods, filtering methods, so that we know that oh, this feature is okay, it's consistent. So we can see these 4 or 5 selected features are very consistent across all methods. So we can use that one for machine learning modeling in the time to come. So thank you so much for listening, and I hope you enjoy the class. You can like it, you can share it, you can also subscribe if you are not yet subscribed. I will see you in the next class. We'll be looking at more interesting topics under this same heading. Thank you so much for listening. I will see you in the next class.